In the last lecture, you would have studied about the Taylor series. The greatest disadvantage in the Taylor series is that if f of z has a singularity at z is equal to z naught, then we cannot expand f of z as a power series in z minus z naught. To overcome this, we have a new expansion called as the Laurent series expansion. Even if z is equal to z naught is a point of singularity, we expand f of z in power series of z minus z naught. Here in Laurent series expansion, you will have positive powers of z minus z naught as well as the negative powers of z minus z naught. The statement is given here. Suppose C0 and C1 are two contours by positively oriented circles implies in the anti-clockwise direction centered at a point z0. Okay, and if f of z is analytic in between these two contours C0 and C1, then each point in the domain can be expressed as a power series in z minus z naught, which is given here, where the constants an and bn are given in terms of contour integrals. Usually in the Taylor series, what we did was we calculated an. Okay, here you have two types of constants, an and bn, where an is the coefficient of z minus z naught whole power n when n is positive, and bn is the coefficient of z minus z naught whole power n when n is negative, and both an and bn are given using this contour integrals. Now what we do is, you can apply the integral and then find the values of an and bn, but that is going to be difficult, or that will be a time consuming process. So to find the Laurent series expansion, what we do is we use the well-known series like 1 minus 1 by z, expansion of 1 minus 1 by z, 1 minus 1 by z whole squared, or 1 by 1 minus z whole cube, or e power z, or log of 1 plus z. So you can use the standard expansion to find the Laurent series of a given function f of z. In the case of the Laurent series, you have a series involving negative powers of z minus z naught. The terms containing the negative powers of z minus z naught is called as the principal part of the Laurent series. And why this Laurent series plays a greater role is that, depending upon the number of terms in the principal part, you classify the type of singularity, which we will be seeing in this particular lecture, type of singularity. So first, one thing that you have to keep in mind is that the negative powers of z minus z naught is called the principal part of the function f of z at z is equal to z naught. And of course, this you already know. If f of z is equal to z minus z naught whole power m, where g of z naught is not equal to 0, then z is equal to z naught will be a root of the function f of z, or it is also called as the zero of the function of order m, because you have z minus z naught whole power m. So it is called as zero of order m. And the next one is the singularity, which we have already seen. A point z is equal to z naught is called as a singular point if f of z fails to be analytic at z naught. Okay, it is analytic at z naught, but it will have a analyticity at some point in every neighborhood. Then such a point is called as the singularity. And if it is isolated, then it is called as an isolated singularity. Okay, except at z is equal to z naught, it is analytic at the neighborhood of that point, then that point is called as an isolated singularity. So the first classification of the singularity is called as the isolated singularity. Okay, and this has got nothing to do with the principal part in the Laurent series. Okay, so now, as I told you that Laurent series plays a vital role in identifying the singularity, and for finding that a singularity is isolated, you don't require the Laurent series. Instead, you have to find that the function is not analytic at z naught, but analytic at neighborhood of every point of z naught. Then such a singularity is called as an isolated singularity. And here we introduce a term called as residue. What is residue? Residue is nothing but the coefficient of 1 by z minus z naught. That is the coefficient of B1 in the Laurent series expansion at z is equal to z naught is called the residue of the function f of z. And as I told you, the principal part helps to find or distinguish between the singularity. The first one is called as the pole. What is this pole? If the principal part contains finite number of terms and the remaining number of terms vanishes, then it is called as a pole of order m. We can see here, instead of having an infinite number of terms in the negative powers of z minus z naught whole power m, you have a finite number. Here you have m plus 1 terms. M terms plus 0. When n equal to 0, you have this m plus 1 terms. And if the number of terms is finite, then that singularity is called as a pole. And depending upon the order of this, it is called as pole of order m. Here it is pole of order m because Bm is not 0 and subsequent terms becomes 0. The second one is the removable singularity. If you have no principal part, then that singularity is called as an removable singularity. See, now when you look at this function sin z by z, this you call it as f of z. Obviously you know that z is equal to 0 is a singularity. But now what I can do is, I can expand sin z minus z cube by factorial 3 plus z power 5 by factorial 5 minus so on. And I have to multiply this with 1 by z. Now when I do it, I will have 1 minus z squared by factorial 3 plus z power 4 by factorial 4 minus so on. You can see here in this expansion, you don't have any negative powers of z. 1 by z, 1 by z squared, 1 by z cube are missing. Therefore here z is equal to 0 is called as an removable singularity. So if you want to identify as removable singularity, you have to expand the given function at z is equal to z not using Laurent series. And if the Laurent series do not contain any negative powers of z minus z naught whole power n, then such a singularity is called as a removable singularity. The third one is essential singularity. What is this essential singularity? If the principal part contains infinite number of terms in the principal part of the Laurent series expansion, then such a point z is equal to z naught is called as an essential singularity. For this, you take this example, f of z is e power 1 by z. Okay. So now if you look at this, I will have e power 1 by z has to be expanded. This will be 1 plus 1 by z by factorial 1 plus 1 by z whole squared by factorial 2 plus so on. Okay. Oh, this one would be better. Z, when I multiply this, I'll have z plus 1. Z into 1 by z will become 1. Factorial 1 is 1. And the next term would be 1 by factorial 2 into 1 by z. Because when I multiply z with 1 by z squared, I will have 1 by z. The next term would be 1 by factorial 3 into 1 by z squared plus 1 by factorial 4 into 1 by z cube plus so on. So in this case, even though I have a finite number of terms in z, I have infinite number of terms in the form 1 by z. So here z is equal to 0 is an essential singularity. Now when you look at this function f of z is equal to z into e power 1 by z, only strong minds can identify that z is equal to 0 is a singular point. Otherwise, what we do is you expand e power 1 by z, and when you are able to get an expansion in terms of 1 by z minus a, then you can say that z is equal to a is a point of singularity. And if the Laurent series expansion contains infinite number of terms of the form 1 by z minus a, then that singularity z is equal to a is called as an essential singularity. And here for this function f of z is equal to z e power 1 by z, this as an essential singularity at z is equal to 0. As I told you earlier that B1 is called as the residue, and if the expansion of a Laurent series contains finite number of terms in the principal part, then it is called as a pole of order m. And when m is equal to 1, it is called as a simple pole. Okay. So you will have only one term, b by z minus z naught. And of course here you will have the positive powers an into z minus z naught whole power n plus this will be f of z. Okay. This will be the Laurent series expansion if you have a simple pole. And now Here I have taken z is equal to a. So z0 will be a, and when I multiply this with z minus a, z minus a into f of z, when I calculate this, this will be summation an z minus z minus a whole power n plus 1, where the index runs over n, plus b1. Okay, suppose if I want to find the residue, I have to allow z tends to a, and when z tends to a, okay, so I'll have limit z tending to a, z minus a into f of z. This will be b1. Okay, because this part will become 0 as z tends to a. So if you want to find the formula, if you want to find the residue when z is equal to a, at z is equal to a, you have to use this formula, limit z tending to a, z minus a into f of z is equal to b1. This is the formula to find the simple pole, to find the residue at a simple pole z is equal to a. Now you have z is equal to a is a pole of order m. Okay, if it is a pole of order m, you can see here this contains finite number of terms, m plus 1 terms. N is equal to 0 to n is equal to m bn by z minus z0 whole power n. Now how do you calculate the residue? What is that? You require b1. Okay, we have to calculate b1. So the principal part will contain b1 by z minus z0 plus b2 by z minus z0 the whole square, plus so on. The last term would be bm by z minus z0 whole power m, and of course you have here summation an z minus z0 whole power n. Okay, and this will be your f of z. Okay, now what I do is I multiply z minus a whole power m with f of z. Okay, and this will have summation, okay, an z minus z0 whole power m plus n plus z minus z0 whole power m into b1 plus so on. Last term would be bm. Okay, I want to calculate b1. So now what I do is, it has to be z minus z0. What I have to do is I have to differentiate m minus 1 times this. Okay, I think here you will have m minus 1, because already I have z minus z0 in the denominator. When I multiply this with z minus z0 whole power m, I will have z minus z0 whole power m minus n b1 plus so on. So when I differentiate this, so automatically I will have the formula here, d power m minus 1 by dz power m minus 1 of the term an dot dot dot, and this will be factorial m minus 1 b1. Okay, when I differentiate once, I will have m minus 1 z minus z0 whole power m minus 2. When I differentiate it again, I will have m minus 1 into m minus 2 into z minus z0 whole power m minus 3 into b1. So when I differentiate this m minus 1 times, I will have factorial m minus 1 b1, and all the remaining terms will become 0, because I have multiplied this with z minus z naught whole power m. So I'll have the coefficient of b2 to be z minus z naught whole power m minus 2, and when I differentiate m minus 1 times, it will become 0, and therefore the term subsequent to z minus z naught whole power m minus 2 into b2 will become 0. So now what I will do is, when I allow z tending to a, this part will also become 0, as z tends to z naught or z naught or a, as the case may be. Z tends to z naught, then that will give you the required value of b1. Okay, so z tends to z naught, that will give you the required value of b1. So when you have a pole of order m, then b1 will be 1 by m minus 1 factorial into limit z tending to a d power m minus 1 by d z power m minus 1 into z minus a whole power m into f of z. So you have to remember these two formula, okay, for finding the residues, because later we will be proving a theorem called as the Cauchy residue theorem, and this Cauchy residue theorem helps us to evaluate certain real integrals, and if you want to use the Cauchy residue theorem, you should know the method to find the residue of a function f of z. So if it is a simple pole, multiply f of z with z minus a and then allow z tends to 0. If it is a pole of order m, then 1 by m minus 1 factorial into limit z tending to a d power m minus 1 by d z power m minus 1 of z minus a whole power m into f of z will be the formula, if it is formula for finding the residue if it is a pole of order m. The third formula is independent of the Laurent series. Suppose if you have a function f of z which is rational p of z by q of z, where q of z is not equal to 0, okay, then it has to be not, and if q of z is not equal to 0, then residue is very simple, okay, p of z by q dash of z naught, okay. Here q of z naught should be 0, okay. I think I have made an error here. P of z, f of z will be p of z by q of z, okay, and this q of z naught will be 0. Why this q of z naught is equal to 0? If q of z naught equal to 0, then you can say that z naught is a singular point. Z is equal to z naught is a singular point of f of z, okay, of f of z. But of course, if you want to use the formula will be like this: residue of f of z, okay, will be p of z naught by q dash of z naught. Here this q dash of z naught is not equal to 0, okay, that you have to keep in mind. Okay, this should be not equal to 0, okay. So in this case, what we do is, residue of f of z is equal to z naught will be the formula p of z naught by q of z, if you have a rational function, okay. So as an example to this, we calculate the residue of z by z power 4 at z is equal to z naught is equal to 1 plus I, okay. So in this case I will have z power 4 plus 4 is equal to 0. This will be taken as the singularity, and z power 4 will be minus 4. Okay, and I can rewrite it in terms of like this. I can write this as 4. Okay, cos pi plus 2n pi plus I sin pi plus 2n pi. Okay, and now I can use De Morvis theorem. Okay, whole power 1 by 4, use the De Morvis theorem, and one such residue will be z naught is equal to 1 plus I. Okay, and now you can see that this is a rational function and this will have 4 singularities, but I am calculating the residue at the singularity z is equal to 1 plus I. So I retain this z in the numerator and differentiate z power 4 plus 4. That will give you 4z cube, and I substitute the point z is equal to 1 plus I. So I will have residue as 1 by 4 z square, and this will be 1 by 4 into 1 plus I the whole square. Okay, so this will be 1 by 4 times okay, I have to expand this 1 plus 2I minus 1. Okay, is that right? I squared will be minus 1. So minus 1 and plus 1 gets cancelled, giving you the answer 1 by 8I. Okay, so the residue will be 1 by 8I. Okay, but here I have written different value. Okay, 1 by 8I, and that will be minus I by 8, but I think I have given here minus 1 by 8. It's not minus 1 by 8, it has to be minus I by 8. So this will be the method to find the residue when you have a rational function f of z. The second example, this will be more interesting because you have f of z is equal to cot z, and I can rewrite this cot z as cos z by sin z. Okay, I can rewrite it as cos z by sin z. So this is a rational function, and here when I take z is equal to 0, okay, z is equal to 0, you have sin 0 to be 0. Okay, but it has got more singularities. When I take z is equal to pi, sin pi is also 0. So automatically when you look at this, it becomes 0 at this axis. N is equal to 0, or 2 pi, or 4 pi, so on. And this will be pi, 3 pi, so on. So that is given here. So singularities of f of z are n into pi, where n takes the value 0, plus or minus 1, plus or minus 2, and so on. And moreover, I have rewritten it in terms of the rational function cos z by sin z. So residue will be cos z by, okay, so it will be cos z divided by differential of sin z, again this will be cos z. Okay, so whatever be the residue, whatever be the singularity, cos z by cos z will become 1. So in this case, what happens here is that residue of f of z is equal to cot z is always 1. Okay, so in this case, you can see here, I would have given q dash of z is cos z, and residue of f of z, namely cos z by cos z, that will also be 1. Okay. So let me recall what we have discussed in this particular lecture. Okay. We saw the advantages of the Laurent series, okay, and the negative powers of z minus z naught whole power n is called as the principal part, and this principal part helps to identify the type of singularity. We discussed what is meant by an isolated singularity, that is, in a particular region only one point do not have its derivative and all the neighboring points has derivative or analytic, then that type of singularity is called as an isolated singularity. The next singularity we discussed was removable singularity. What is meant by removable singularity? If it does not contain any terms in the principal part, then in that case you call it as the removable singularity. Example that was given here was sin z by z, and the third type is called as the essential singularity. What is this essential singularity? The example that was given here was e power 1 by z, that contains infinite number of terms in the principal part. So these are the varieties of the singular point. If it has finite number of terms, okay, if the principal part in the Laurent series expansion contains finite terms of z minus z naught whole power n, okay, where n is negative, then you call it as pole of order z is equal to z naught is a pole of order m. Okay, and we had given three formulas to find the residue. Okay, if it is a simple pole, formula 1 has to be used. What is this formula 1? You have to just calculate z minus a into f of z as z tends to a. Okay, if it is pole of order m, then you have to use the formula 1 by factorial m minus 1 d power m minus 1 by dz power m minus 1 z minus a whole power m into f of z. You have to use this. And if you can rewrite the given function as a rational function f of p of z by q of z, then the formula will be p of z naught divided by q dash of z naught, and q dash of z naught should be non-zero. So all these things has to be remembered, so that we will be using this in the subsequent lectures. We will be calculating the residues, we will be identifying the type of singularity, and using the calculation of residues we will evaluate certain integrals using Cauchy residue theorem, and using Cauchy residue theorem we will evaluate certain real integrals. And all these will be discussed in the subsequent lectures.